10.3 Angular and Translational Quantities. The outline of this video is as follows. Our main goal is to understand the different types of acceleration experienced by a point on a rotating object. To get there, we will first explore the crucial connection between angular speed, which describes how fast something spins, and tangential speed, which is the linear speed of a point on the object's edge. Next, we will extend this to acceleration, relating the angular acceleration of the object to the tangential acceleration of a point on it. This will lead us to a complete picture of total acceleration, including the radial or centripetal component. Finally, we will apply all these concepts to a practical example, the physics of a compact disc player, which cleverly adjusts its rotation speed to read data at a constant rate. Now we will build a bridge between the rotational motion of an entire object and the translational, or linear, motion of a specific point on that object. This is essential for describing how different parts of a rotating body move through space. The fundamental principle is that when a rigid object rotates around a fixed axis, every particle within that object moves in a perfect circle. Crucially, the center of each of these circular paths lies directly on the axis of rotation. If we consider the velocity of any single point, its direction is always tangent to its circular path. For this reason, we call it the tangential velocity. For example, on a spinning record, a point near the outer edge traces a large circle, while a point near the center traces a much smaller one, but both circles are centered on the axis. Therefore, understanding the circular motion of its individual points is the key to connecting an object's overall rotation to the linear motion we can observe. Let us establish the crucial link between the linear speed of a point on a rotating object and the object's overall angular speed. We start with the definition of tangential speed, v, as the time rate of change of the arc length, s. From geometry, we know that arc length is the radius, r, multiplied by the angle in radians, theta. For any specific point on a rigid object, its radius r is constant. So when we take the time derivative of the arc length, v equals ds over dt, the constant radius r comes out of the derivative. This leaves us with v equals r times the quantity d theta over dt. We have already defined d theta over dt as the angular speed, omega. This gives us our final, simple relationship. V equals r times omega. For example, on a merry-go-round, a person on the outer edge has a much larger tangential speed than a person near the center, even though both have the same angular speed. Therefore, while every point on a rigid object shares the same angular speed, their tangential speeds are directly proportional to their distance from the axis of rotation. The acceleration of any point on a rotating object has two distinct components, tangential and radial, because the point's velocity can change in both its magnitude and its directions. First, let us consider tangential acceleration, labeled as sub t. This component is tangency to the circular path and represents a change in the object's speed. We find it by taking the time derivative of the tangential speed, v. Since v equals r times omega, the tangential acceleration simplifies to r times alpha, where alpha is the angular acceleration. This means tangential acceleration only exists if the object is speeding up or slowing down its rotation. Next, we have radial acceleration, labeled a sub r. This component is always directed toward the center of rotation. Even if an object rotates at a constant angular speed, its velocity vector is constantly changing direction. This change requires an acceleration, which we also call centripetal acceleration. Its magnitude is given by the fraction v squared over r, which can be rewritten as r times the quantity omega squared. In short, tangential acceleration changes the rotational speed, while radial acceleration is what keeps the point moving in a circle. Now that we have expressions for both the tangential and radial components of acceleration, we can find the total acceleration for any point on a rotating object. The key insight is that these two components are always perpendicular. The tangential acceleration, a sub t, points along the path of motion, changing the point's speed. The radial acceleration, a sub r, points toward the center of rotation, changing the point's direction. Because they form a right angle, the total acceleration vector, a, is their vector sum. To find the magnitude of this total acceleration, we use the Pythagorean theorem. The magnitude a is equal to the square root of a sub t squared plus a sub r squared. As the slide shows, we can substitute our previous formulas for these components, which simplifies to r times the square root of alpha squared plus omega to the fourth power. Therefore, the total acceleration of a point depends on both the object's angular speed and its angular acceleration. Let us test our understanding of angular speed with a classic example involving a merry-go-round. This question highlights a crucial property of any rotating rigid object. A merry-go-round is a good approximation of a rigid object, which means all of its points are fixed in position relative to each other. As it spins, every single point, from the center to the outer edge, must sweep through the same angle in the same amount of time. If a point on the outside rotated through a different angle than a point on the inside, the merry-go-round would have to stretch or break apart. Since angular speed is the angle covered per unit of time, it must be the same for all points. Therefore, even though Ethan is twice as far from the center as Rebecca, his angular speed is identical to hers. The correct answer is B. Now let us address the second part of the quiz, which asks us to compare the tangential speeds of Ethan and Rebecca. This concept is important because, unlike angular speed, tangential speed depends directly on the distance from the center of rotation. We know the relationship between these quantities is that tangential speed, v, equals the radius, r, multiplied by the angular speed, omega. From the first part of the quiz, we established that because they are on the same merry-go-round, both Ethan and Rebecca have the same angular speed. However, the problem states that Ethan is at twice the radius of Rebecca. Since tangential speed is directly proportional to the radius, Ethan must have twice the tangential speed. Imagine the path they trace. In the time it takes to complete one revolution, Ethan has to travel along a much larger circle than Rebecca. To cover that greater distance in the same amount of time, he must be moving faster. Therefore, the correct answer is A. The essential result is that for a rigid rotating body, tangential speed increases linearly with the distance from the axis of rotation. The key physical principle for a CD player is that it must read data at a perfectly steady rate. This means the section of the data track moving past the laser must have a constant linear speed, which we call the tangential speed. For a typical CD, this speed is held constant at 1.3 meters per second. We can relate this to the disk's rotation using the equation v equals r times omega, where v is the tangential speed, r is the radius, and omega is the angular speed. As the CD plays, the laser starts at a small radius near the center and moves outward to a larger radius at the edge. To keep the tangential speed, v, constant while the radius r is increasing, the angular speed omega must decrease. Therefore, a CD must spin faster at the beginning of the disk and progressively slow down as it plays towards the outer edge. In this first part of the example, we will calculate the required angular speeds for a CD at its innermost and outermost tracks. This is necessary because a CD player must maintain a constant tangential speed where the laser reads the data. We start with the relationship that tangential speed, v, equals angular speed, omega, times the radius, r. For the innermost track, we find omega by dividing the constant tangential speed of 1.3 meters per second by the inner radius of 0.023 meters. This gives an initial angular speed of about 57 radians per second. The problem asks for revolutions per minute, so we convert units, which yields a speed of about 540 revolutions per minute. Next, we repeat this process for the outermost track, which has a larger radius of 0.058 meters. Dividing 1.3 meters per second by this radius gives a final angular speed of about 22 radians per second. Converting this to revolutions per minute gives approximately 210. To keep the data moving past the laser at a constant speed, the disk must spin more than twice as fast when reading the inner tracks compared to the outer tracks. Now let us find the total number of revolutions the disk makes during its full playing time. This requires us to calculate the total angular displacement over that period. First, we need the total time in standard units. A playing time of 74 minutes and 33 seconds converts to 473 seconds. To proceed, we will model the disk as a rigid object under constant angular acceleration. This simplifying assumption allows us to use a familiar kinematic equation. Specifically, the angular displacement, delta theta, is the average angular speed multiplied by the time interval. Using the initial and final speeds of 57 and 22 radians per second from part A, we calculate a total displacement of 1.8 times 10 to the power of 5 radians. Finally, to answer the question, we must convert this result from radians into revolutions. We do this by dividing our angular displacement by 2 pi radians per revolution. This calculation shows that a standard CD spins approximately 28,000 times to play all the music on it. Now for the final part of this example, we will calculate the angular acceleration of the compact disc over its full playing time. Since we are modeling this as a system with constant angular acceleration, we can use its definition. Angular acceleration, represented by the Greek letter alpha, is the change in angular speed divided by the time interval over which that change occurs. From our previous work, we know all the values we need. The final angular speed, omega f, is 22 radians per second. The initial angular speed, omega I, is 57 radians per second. The total time interval, delta t, is 4,473 seconds. Plugging these into the equation, we have the quantity 22 minus 57, all divided by 4,473. This gives us an angular acceleration of negative 7.6 times 10 to the power of negative 3 radians per second squared. The result is a negative number, which makes sense because the disk is slowing down. It is also a very small number, which tells us that this slowdown is extremely gradual as the laser moves from the inner track to the outer track. This slide summarizes the essential equations that connect the linear motion of a point on a rotating body to the body's overall angular motion. These relationships are fundamental for describing how individual parts of an object move as it spins. First, the tangential speed, v, of a point is directly proportional to its distance from the axis of rotation, r, and the body's angular speed, omega. This is why a point on the outer edge of a spinning disk travels faster than a point near the center. Next, we consider acceleration, which has two distinct components. The tangential acceleration, a sub t, is caused by a change in the angular speed. It is equal to the radius, r, times the angular acceleration, alpha. The radial, or centripetal acceleration, a sub c, is what keeps the point moving in a circle. It is always directed toward the center of rotation and is given by r times omega squared. Finally, because the tangential and radial components are perpendicular, we can find the magnitude of the total linear acceleration, a, using the Pythagorean theorem. This results in the equation A equals r times the square root of the quantity alpha squared plus omega to the fourth power. Let us pause and apply what we have learned with these two review questions. They test our understanding of tangential and radial accelerations. For the first question, consider a car tire rotating at a constant angular velocity. The key phrase here is constant angular velocity. This means the angular acceleration, alpha, is 0. What does this imply for the tangential acceleration, which equals the radius r times alpha? For the radial acceleration, recall that it is equal to the radius r times the angular velocity squared. Since the gum is on the tread, it has a non-zero radius, and the tire is spinning. Is the radial acceleration 0? For the second question, two children are on a merry-go-round that is speeding up. Speeding up means there is a non-zero angular acceleration, alpha, which is the same for both children. To find who has the greater tangential acceleration, compare the quantity r times alpha for child A near the center and child B on the outer rim. To find who has the greater radial acceleration, compare the quantity r times omega squared for each child at the same instant. Take a moment to work through these problems, as they highlight the critical role that radius plays in relating rotational motion to the linear accelerations experienced by different points on a rigid object.